Good. So I'm going to go over a few slides, but this is one of the crucial parts of this class. We have already made some important predictions in this class. We made predictions about the transition from spray to globular to spray transfer. We made predictions about the position rate of a weld, right, in a wire-based process. And what other predictions we have made? We can predict when we can have a repelled transfer. We can do powerful stuff. What I want to share with you now is the work that has come from our lab in the last few years, in which we have made an enormous effort to get to this point. And although these formulas are published in important papers, we are using these, and the hope is that they will become standard worldwide. The formulas we're going to discuss are the formulas that are the basis of most codes and standards, like the AWS D11 or the German codes or the British codes are based on some of these formulas. But typically, those formulas apply only to steel. We decided to go deep, and what we have is good for pretty much everything. So, and about temperatures. Some things that seem to be just pure metallurgy, like the heat affected zone, in the end, comes back to temperatures. And that's one of the questions I asked in the exam last week, right? So at what temperature we have the intercritical zone, at what temperature we start to have an edge of heat affected zone. If we understand the temperature, we can make predictions about temperatures in welding, then we can make predictions about size of heat affected zone. Then things are a pretty big deal. So temperature in welding, right, is one of the most fundamental aspects. And if you remember, we discussed this, is this non-equilibrium feature of welding, in which part of the metal is molten and part is not molten. And it's amazing. In casting, everything is molten. In forging and machining, nothing is molten. And in welding, you want to be at one happy medium. And it's just like a miracle of God that with the little understanding we had 100 years ago, we managed to melt only part and not all, and at least melt something, and not just be frustrated that we couldn't melt anything. Because some is molten, some is not. This is in non-equilibrium because the heat goes from the hot to the cold, and we have this very delicate balance between how do I keep some molten, some not, and I need to understand how the heat is moving from one place to the other. That will end up with gradients, transients, time constants. If we look at these transients, right, we can look at the transient of just one point that was hot and cooled down. There's a theoretical model for that. Actually, it's the simplest of all. I'm not going to bring those formulas now because I don't want to have too many things that can confuse you. But this hot point that gets hot and then cools off, right, is what happens in an arc strike. An arc strike is when the welder, by mistake, or it's always by mistake, would sometimes touch the arc against a piece of steel, and there's a short arc, but the welder realizes, pulls the arc back. Okay, just what could happen? Only something very brief. Well, in an arc strike, the heated area is so small that cools down very fast, and that tends to be kind of a hard point, your base material, which can end up with cracking and failure. just out of that arc stripe that looked like such an innocent mistake. The mathematical model of that is a point that goes hot and cold, right? Or releases heat in a flash. If instead of saying I release heat in a flash at a point, I release heat in a flash along a line, that looks very contrived, right? But that is pretty much the model that would represent very fast welds, right? Interesting. I'm talking about like the ways in which we can idealize the incredible complexity of a real weld. We can have a point in 1D, right? And in 1D, this is the case of the semi-infinite solid we have seen in our welding class. And in this case, something gets hot on top of a volume, and then the heat diffuses in. That might seem crazy to you, but there is a patented process that people call like mesocoat, and they want to make overlays. They have something like a flashlight, but it's enormously powerful. So you put like on top of a metal, you put your powders, you flash this light, it's so powerful, it melts everything on the surface. Done. We have one of those systems here in Edmonton at MatE. I'm not too sure how much use it is, but it's interesting to know. This flash over a whole area is used to do NDT in composites. Those of you who took the heat transfer class with me know that if I put heat on the surface of a semi-infinite volume, the heat will diffuse in. So if I put this heat very briefly, it will go in and I'm gonna see the surface cools down. But if I have delamination, the heat cannot jump across the delaminated area, and we're gonna see a hot spot. This is the way you test for delamination in aerospace composites, right? Very interesting. And all this comes down to very, very basic formulas that of the type we have seen in the heat transfer class. Not much more sophisticated than that. It's just knowing what we do and having the right equipment. In addition to this type of flash heat sources, we can have moving heat sources. For example, let there be a point moving over a semi-infinite solid, or let there be a point moving over a thin plate, right? There's even one, let there be a point moving along a wire. These three, which of course are like quite significant idealizations, especially moving on a semi-infinite solid, which would be more or less the same as moving over a very thick plate or moving over a thin plate. Those two are going to be the basis of these formulas we're going to discuss. The formulas we're going to discuss look very, very much similar to the formulas we did in the heat transfer class. There are other types of heat sources too. Instead of being a point, I can have like a hot area that is moving, and the area could be have a heat density distribution that is Gaussian or a top hat. The sky is the limit to how many variations we can have. In this class, we're going to look at only those two types of heat sources: moving heat sources in 3D and moving heat sources in 2D. And we will be able to say lots. Okay, what is the difference between 2D and 3D? These are cross sections of the weld. In a 3D heat source, we have the heat that in the cross section goes into the depth and to the width of the weld, right? So a semi-infinite solid, it definitely goes in all directions, but if the plate is thick enough, the heat coming at the bottom is going into the bottom without knowing that there is an end at some point. How about 2D? In 2D, we can have two possibilities. For 3D, we have only one possibility. The substrate is very thick. In 2D, we have two possibilities. One, the plate is very thin, so the heat can only move along in 2D because the plate is 2D. That's one possibility. Another possibility, the plate is very thick, but I'm having my heat source has a deep penetration, so it's like a line penetrating in there, right? For example, the case of keyhole in lasers or electron beams. And we have this schematic here. And in this case, the heat doesn't go top to bottom because the whole weld penetrated all through it instantly. And the weld moves to the sides, even if the plate is thick, right? So the criterion for thick and thin of 2D, pretty much all thin plates are 2D. But the thick plates can be 2D or 3D, depending on the configuration of the penetration. In general, most welds that are single pass welds will be 2D. And the reason is because I'm penetrating all through the thickness. And of course, there are intermediate cases. And in the intermediate cases of thickness, here we have the isotherms. And for that, I do not have formulas to share with you. There are some in the other research papers, but nothing that you can use in a practical way. So in this class, we're going to consider, is the plate very thick or is the plate very thin? And for the intermediate cases of thickness, right now, we're going to say, we'll figure out later. We are not in a bad situation at all. Questions related to temperature. How about cooling rate? If you remember when we did Yurioka, the T85 was one of the key elements to get that we needed to predict hardness. I'm going to teach you how to predict a T85. Reverse engineering. If I give you a cross section of a weld, what was the heat input? We have already discussed, right? It's more or less 0.6 joules per kilojoules per centimeter per square millimeter, right? But that was related to welds in which we were melting a consumable. But if it is autogenous, that's tough. But I'm going to show you how to reverse engineer a procedure. Question, how does preheat affect the heat affected zone? With more preheat, should I have bigger heat affected zone, smaller? How much bigger? Very practical questions. So these curves might look a little bit complex, but I think these curves are the engineering expression of something that is already in our intuition. So let's say we have a butt joint here on this plate. This is a cross section of the weld. This is a single pass weld with we don't know if actually how the joint was prepped because this is a cross section that melted. And here, let's say we put 1, 2, 3, 4 imaginary thermocouples, temperature sensors next to the weld, right? So we are gonna weld and we're gonna see a number of things. Let's talk about what is in the graph on the right first. So thermocouple number 1, that is right next to the fusion zone, would reach the melting temperature, and after the weld comes, will cool down. Yeah. Thermocouple number 2, and we saw this when we talked about heat affected zone, is going to heat up, but the maximum temperature is going to be lower. For sure, this one is not melting because I know melting reach only up to here. So it reaches a high temperature and comes down. Number 3 is the same story, but the maximum temperature is lower and lower and lower, right? And these curves we have here is how we see as the torch comes in temperature goes up, torch passes, temperature starts to cool down. The T85 would be, here is not marked the temperature, right? But from 800 degrees to 500 degrees, wherever those would be. Okay, let's look at this graph on the left. This graph on the left says that right when the torch, this figure on the left is unrelated to the thermocouples. We can forget the thermocouples. But what it says is right when the weld, the torch is, in these graphs, they take only, let's make a line perpendicular to the line of welding, right? That would be like a line of a cross section. And at one point, the torch is right over that line. So it's very hot. This is melting temperature. And then after the torch passed that line, right, past my cross section, the temperature starts to come down. But it comes down in a very interesting way, very related to the semi-infinite solid of the heat transfer class. As this comes down, heat penetrates in. So the maximum temperature goes down and down and down and down. But the temperature just outside the weld, in some cases, the temperature goes up because the heat is going out as it distributes out. So we would see that the cross-section in a distribution of temperatures in welding looks like this Gaussian here. Doesn't need to be a Gaussian, but looks like this curve that opens up. As it opens up, the top is, the peak is reduced and the width is expanded. Here we have an image we took in our lab about pipe welding. And I don't know, this might have been during the times Eddie was in the lab. Now we have a even better thermal camera than this. What we see here, as we were welding, we were welding from the top to the bottom, vertical down in this case. You see the white is really, really hot. Don't pay attention to these numbers because the machine was not calibrated. But we know that this was very, very hot. And as we move back, this very hot white area gets thinner, right? And the yellow is the other, is at slightly lower temperature, the red, the purple, lower and lower temperatures. What we see here is something interesting, that the isotherms, right? The lines of the same color, if I were to pick a color and I make a line, those lines run pretty much parallel to the weld, right? That means the isotherms are very, very elongated, right? That's characteristic of a fast weld, and I'll show you more. We already saw this when we discussed heat affected zone, and this is what we're going to be talking about now. In heat affected zone, we talked a lot about the iron carbon phase diagram. Now we're going to talk about the heat transfer that gives us these curves. How do I get, and if I have a question related to temperature, how do I get an answer? 90% of the times, you go and weld again, and typically you'll figure it out. This class is not for the 90% of the times. This class is for when you're 10% of the times you say, what do I do here? One alternative is numerical analysis. So you go, you do your PhD in finite elements or computational fluid dynamics, and you can make a simulation like these ones here that looks so beautiful. In general, these beautiful, beautiful predictions do not match reality by a long shot. And when they do match reality, do you know how it is? They ask you for the experimental results, then they tweak their parameters. And after you give them the experimental results, they say, yeah, you see, I match it perfectly. And then, as long as you don't move too far from that perfect match, they are kind of okay. But if you say, oh, okay, how about if I change steel for aluminum? Well, you better start making aluminum experiments so so they can calibrate things. Now, these things that look beautiful and look so rigorous, and they have lots of little skeletons in the closet. People think they're so accurate, but they're not so accurate. There are other things like these Rosenthal solutions that people think they're not so accurate. And you know what? They're equally accurate, especially after you calibrate them. And these Rosenthal solutions is a guy who most people attribute with having solved the heat transfer equation. And this is what the formula would look like. We'll discuss this in a minute, right? And these solutions are formulas. And you plug these formulas and you get results. Rosenthal didn't invent this formula, it was invented years before. So look at this. I want to share with you one of the cool things of using formulas in welding. Let's say that we want to we want to design something. Let's say we want to design a jet fighter or the Concorde or something like that. If I'm going to design an airplane, the cost of the prototype, and you can check it out on the Wikipedia, but designing a new plane is of the order of $10 billion. $10 billion. Now, my question to you is, all right, how about if I crash enough planes until one flies? Nobody would think of doing that. Everybody would think, are you crazy? That's why we have engineering for, right? Let's do some simulation. And for sure, because of simulations or wind tunnel or whatever you do, it's not going to be $10 billion. So you do it. And you do the aerodynamics, the fluid mechanics, viscous fluid, the inertial flow, all that stuff. Now let's say you have a weld and you say, how do I figure out this weld? Well, this is interesting because if I want to do a weld, depending if I have the machine, if we have it in the lab, cost us between $0 and a few dollars. I want to say $1,000 to test the weld, right? Now, if I tell you, no, let's do like we do airplanes, let's do a simulation. The simulation, and I know from our adjunct professor in our center, Professor John Goldak, he's the father of numerical simulations. He has spent about $10 million in developing software for simulating welds and about 500 person-years, right? When I tell you that, don't you feel like, you know what? Thank you very much. I'm going to go plug in my machine and see if it works or not. Sometimes you need to do the simulations. For example, Professor Goldak was very involved in the repairs of the CANDU reactor and the Victoria-class submarines. You really want to simulate there because a submarine is more or less like an airplane. You don't want to break enough until it works. But most of us who are not doing nuclear reactors or military or submarines, okay, so for airplanes, the prototype is very expensive, simulation is cost effective. For welding, a prototype, which is another weld, is cheap and simulations are expensive. So at some point, things cross over. And at some point, it's like even whether you just do trial and error or you simulate it. Now, if we, for example, in the way we teach in this class, we can make formulas such that the cost of the prediction is much lower than a simulation. Instead of being the $10 million of developing software, we have a formula that you can do in Excel, right? All of a sudden, we're moving the crossing point, then still at some point, if you need to weld a fence, you might as well just go and weld it. But if you need to weld a pressure vessel and you don't want to spend a PhD in doing the finite element simulation, you can have a formula that helps you make those predictions, right? That's the type of work we're doing, doing something in which we're moving the point of just try it again to much simpler cases, and cases in which you cannot justify numerical simulation. You can still say, you know what, I'm not going to do something so expensive, but I will do something smart. And that is good engineering. So Rosenthal solutions are the basis of these formulas. What did Rosenthal do? Rosenthal did a number of things that offend the common sense of most people. But the funny thing is, all these simplifications he made are quite okay. So I'm going to say a number of things that sound crazy, but the results we get are very reasonable results. What sounds crazy? Well, he says, let's say the torch moves in a straight line at constant velocity. There are ways of accounting for weaving. Let's not worry about that right now. Like you can have some sort of kind of average velocity. But so if you're doing a weld that has kind of a complicated shape, this is not the model. But for the most part, most welds, even welds around in a pipe, can be considered like a straight line, right? It's like if the pipe has a large enough diameter, it's like the surface of the earth that looks flat to us, but it's not. The other thing is he's considering a pseudo steady state, right? In fancy terms, those of you who took the heat transfer class, these are the Eulerian coordinates we talked about. So he says, if I put my axis of coordinates at the torch, then as I move the torch, I don't see much of a change, right? This means let's forget about the problems at the start of a weld, and let's forget about the problems at the end of a weld, which we can also deal with, but I don't want to deal with those right now. He says also that plate is infinite in length and infinite in width. Okay, the day you find an infinite plate, let me know, because we'll sell it and make a lot of money. But this is what the solutions are for infinite length and infinite width. Sounds crazy, but most plates are about the right. Most cases are about the right. For most welds, this is a good consideration. He assumed that the plate is then, the heat transfer is either 2D that is very thin, 3D that is very thick, or 2D that is the case of either very thin or a keyhole penetration. He also said that the heat source is so small that it's just a point heat source. In 3D, it's a point on the surface. In thin plate, it's just a point on the thin plate. In a thick plate, 2D would be a point if you look at it from the top, but in reality, it's a line that penetrates, right? It says it doesn't have like a size, the heat source. Also says thermophysical properties are constant, which is kind of okay until you say, aha, and no latent heat? No latent heat. He says no latent heat. Go figure. But this simplifies the math very much. And the cost we pay in accuracy is not very high. Heat losses to the environment. So we know convection and radiation and all those things in something as hot as a plate being welded. For the thick plate, he says that doesn't matter. And by the way, it's an awesome assumption. For the thin plate, he says, I have a way of accounting for that, which I don't want to worry you about that now. But we also have formulas for what happens in cases like underwater wet welding, in which you have significant convection losses on the surface. So he says all these things that sound like crazy simplifications, And then did somebody called Christensen in the 60s did hundreds of experiments and cut the welds to see the section. And these graphs here are about, let's not worry about these axes because they are kind of dimensionless groups that are that I don't want to use right now. But he says this is essentially related to travel speed, and this is cross-section of the weld. And what we see that the line is what the formula of Rosenthal predicts. That's the line. And the dots are welds they made. Some MIG, some TIG, some stick, some subarc welding, some in steel, right? And what do we see? We see two things. Number one, the points fall around the line, which means the formulas are pretty good and don't have a significant systematic error. And look, these measurements, these scales are log scale in both axes. So we have from here, 1, 2, 3, 4, almost 5 orders of magnitude. So if one weld had whatever property that was 1, there's another weld they did that has a property of the order of 100,000. And over that, the dots fall on the line. An amazing feat of engineering. We see something else, scatter. And the scatter is of the order of half an order of magnitude, of a factor of 3. So sometimes this formula might predict a 1 and in reality was a 3, or the other way around, might predict 3 when in reality was a 1. So we have to know that these formulas we're going to be using are not perfect, but for the simplicity they have, they can predict things over 5 orders of magnitude and never be too bad. This is the solution for the moving heat source in 3D. Look at all the things that come in here. T naught, the Rosenthal heat source is temperature as a function of space, and says this is the preheat or interpass temperature, T naught. That's by the time you start welding, that's the temperature the plate was, T naught. So we can already start accounting for preheat. Q is the power of the heat source. That would be, for example, what the heat that gets into a plate would be voltage times current. That's the power that the welding machine gives times thermal efficiency, right? This is the Q related to the procedure. K is thermal conductivity. R is this radial coordinate. U is the welding travel speed. And alpha is thermal diffusivity. X is also a coordinate. So this formula is funny. The researchers say, oh man, this is so oversimplified. You should be doing my finite elements and CFD. Maybe. Then I go to welders and I show them and they say, are you crazy? I don't do trigonometry. And this is not trigonometry, but that's what they tend to call these things that have too many Greek letters. So look, welders tend to shy away from this type of thing. The scientists tend to shy away from this type of thing for a very different reason. And my question to you is, if I take out the welders and I take out the scientists, what do the engineers do? And the funny thing is engineers so far have tended to fall either with the welders or with the scientists. But seldom engineers have done engineering and use a formula. That's what we're doing in this class. So temperature for 3D, the same formula, but for 2D. Here we have the power coming into the plate. In this case, thermal conductivity, D. D is the thickness of the plate, right? Thickness of the plate. And you might ask me, okay, didn't you tell me that the plate is infinitely thin? Well, but then the way if the plate was infinitely thin, the heat you can put in it is infinitely small too. So here we have heat we put in divided by the thickness, And all this comes from solving the equation. So this is not empirical. Travel velocity, space coordinate, thermal diffusivity. Two more things. We will not use this part, but Rosenthal said for thin plate, and this is only for thin plate, not just 2D, but thin plate, I can account for the heat losses from the surface. For those of you guys who took the heat transfer class, he uses a fin approach. And by using the fin approach, he can calculate this. And here we have heat convection coefficient on top of the plate, convection coefficient on the back of the plate. Typically, this might as well be 0, with the only exception of underwater wet welding and a few other uncommon calculations. Number two weird thing, this K naught. K naught is something you might not have seen before, that is called a modified vessel function of order 0, right? That's a mouthful. The good news is if you want it, you calculate it in Excel using this command, right? So now we can calculate temperatures, and we can calculate in 2D and in 3D. Funny thing, you know what it is? Nobody cares about temperatures because I already know my temperatures. I know A1, I know A3, I know melting, that I know. What I don't know is where that temperature is. The question in welding very seldom is what is the temperature? The question is, this temperature I know, where is it? And the problem is very difficult because we need to work these equations backwards. And in few cases, few people have done something like that. We went into industrial scale with this. Look, here we have the isotherms, right? If you remember when I showed you some curves about temperature before, this is now if the weld is, the torch is moving to the right. Here we have, and let's not worry about the axis here. This is temperature, the vertical axis, let's call it temperature, and the horizontal axis, let's call it position. And we see how temperature goes up, then goes down, up and down. And because this is a point heat source, the simplification has a crazy spot. At 0, it says temperature is infinite. Of course, it's not, right? And if we were to look at the isotherms, the lines of equal temperature from the top, right, we would see these curves here that look like ellipses, right? Look like ellipses. And at high temperatures, they look like a little circle around the heat source. And at lower temperatures, they start to get longer and longer and longer. Something interesting. If we are moving slow, then the isotherms look like circles around our heat source. If we move fast, they start to stretch out. And of course, this makes intuitive sense, right? As we move fast, it's like as if it was dragging the heat with it. So this one on the right with the elongated isotherms is a fast heat source. This one with the circular isotherms is a slow heat source. What is fast and what is slow? Okay, I was asked a question, what do the axes mean? These are dimensionless axes. This is the axis in the direction of welding, right? And I'm not gonna be using this notation, but this is the axis in the direction of welding. And this is the axis transverse to welding, right? So this would be, typically we call this X in the direction of welding, and we call this other Y in the perpendicular direction to welding. In this case is dimensionless, the way they did it. What is fast? Fast in steel is very different than fast in aluminum. Very different than fast in titanium. Because how fast I move the torch is only part of the story. How fast the heat moves away from my torch is just as an important part. So fast and slow are not measured in inches per minute. Fast and slow are measured with a dimensionless group similar to the Reynolds number. right? The flow in a pipe is not enough to know if you are turbulent or not, right? You need to know actually the Reynolds number to know if you're turbulent or not. In this case, we don't have turbulence, but we have something similar. Is for the thick plate, the 3D solution, something called the recalling number. And this recalling number, you see it has the velocity here on top, right? If you move fast, the recalling number is high. If I move slow, recalling number is low. Also, if I'm very hot, recalling number becomes small, right? And if I'm cold, recalling number becomes fast. So this combines not only the velocities, but the material properties that we see here and what temperature we care. For thin plates, we have a similar dimensionless group called the Rosenthal number. And the thickness, we can have a dimensionless thickness that we define here with this star. The star means dimensionless. Okay, I'm trying to explain the things here, but let me show you how the mechanics work. This map here is a map of every weld conceivable to humanity. In the horizontal axis, we have this recalling number, which is the number that says, are we fast or are we slow? So on the right, we have everything that would be fast welds. On the left, we have everything that would be slow welds. The vertical axis is the dimensionless thickness of the plate. At the top, we have thick welds. At the bottom, we have thin welds. Now, you would be tempted to say, okay, I divided like in 4 evenly. But if you do a proper analysis, which is outside the scope of this class, but it's part of the PhD work of many of the guys in our lab, you realize that in reality, if you're fast and you're thick, is divided from the fast and thin by a line that is not just straight at 90 degrees. And same like the combination of fast and thick or fast and thin or slow and thick, right? Slow and thick is here, or slow and thin ends up being in this part here. And this matters because a thick weld behaves differently than a thin weld, and a fast weld behaves differently than a slow weld. So if we somehow calculate the recalling number and this D star, the dimensionless thickness, you can tell me, oh, my weld falls here where I have the cursor right now. Oh, that's fast and thick. Or maybe I ended up here. And you'd say, aha, this is fast and thin weld. Our amazing students in the lab did a big effort and went to the welding procedure handbook and transcribed many of those procedures. And what do we see? We see that some things, for example, here we have friction stir welding of aluminum, right? Friction stir welding moves slowly, but in aluminum, the heat moves fast. So if the heat moves fast, so if the torch, if the heat source moves slow relative to the heat in the plate, we say that's a slow heat source. Sure enough, look, in friction stir welding, the welds tend to be fairly slow. Let's look at this. Submerged arc welding, the squares. In submerged arc welding, it's a high productivity process. We have very elongated isotherms. We're moving very fast because we're putting lots of metal and lots of heat. We see that here. MIG of aluminum is a relatively slow process. This circle here is indicating the parts that are kind of intermediate. We are going to, because we don't know very well how to calculate intermediate, we're going to say, if I fall in fast, and thick, I use the formulas for fast and thick. If I fall in fast and thin, I'm going to use the formulas for fast and thin, right? Inside this circle, in reality, is a little bit more complex because things are mixed up. But in the case of the combination, you're never too far from one of these extreme conditions of fast and thick or fast and thin. In this slide, we have typical parameters that I want you to have because they will be your reference to use the formulas. These are the numbers you can plug in to calculate welding of titanium or Inconel or Monel, or hey, why not carbon steel? I showed you, this is the third time I show you isotherms and curves. I'm giving them proper names now. The axis in the direction of welding, I'm going to call X. The axis transverse to welding, I'm going to call Y. This is kind of a mechanical view. This is the weld seen from the top. This is one isotherm. Now, if I look at the temperature profile, I'm going to see that in the center line, I have some heating rate, right? And if I pick a characteristic temperature, Tc, the slope of that curve at Tc is the heating rate or the cooling rate, right? The cooling rate as the weld starts to cool down at Tc, I can give it a characteristic value. And we're gonna call this point, the front point of the isotherm, Xf, the back point of the isotherm, Xb, the width, right? I'm going to call it Y max, right? The maximum width of this isotherm. And the position where this happens, I'm going to call it X max. All right. Look at this. Maybe this slide is the one that looks scariest of all the other slides. This slide is your friend. I've been talking for an hour and 15 minutes. Blah, 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 blah. What I said is nothing compared with what is here. Look, Y max. This is the width of my weld, or the width of my heat affected zone, or this is the width. Very difficult to calculate, either numerically or difficult to do using Rosenthal. But here we have a formula. These regimes 1 or 2, and you're going to see 3 and 4, corresponds to, oh, I didn't mark it here. This is terrible. Okay. Regime 1 is fast and thick, and regime 2 is slow and thick. And this is fast and thin is regime 3, and slow and thin is regime 4. So regime 1, this is when we are fast and thick. And here we can, with this formula, using the things you already know, we can predict the width. This correction factor is for the intermediate cases for speed, but we don't have an intermediate case for thickness yet. So I'm not going to worry in this class about the correction factor, but I wanted you to have it because you can use it in the future. So we're going to be using only this. So if I fall in fast and thick, I can calculate the width this way. I can calculate where the end of the isotherm would be, this XB. Oh, XB is this point here. So it gives me how far behind my isotherm is. If it is the melting isotherm, this gives me an idea of how far the molten metal is. And if I have shielding, my shielding better cover this part here in the back, right? So you see how some of these formulas can start having value. This is cooling rate in the back, degrees per second. And here we have a formula for this cooling rate. This is heating rate, which is not so important in this case. So here we have maximum temperature. Now, all these formulas are for the center line. But if I'm a little bit off the center, for example, I'm a distance, let's call this distance YC, right? I would have a maximum temperature that is not infinite anymore. I have a maximum temperature, and I can calculate that maximum temperature. Here you have a formula. What else? Here we have melting efficiency for the case of a 3D source. Here you have formula for T85. Here you have formula for solidification time. My favorite, which we're gonna do in the seminar in 10 minutes, is thickness of the heat affected zone. We have a way of predicting the thickness of the heat affected zone. That's so amazing. Let's stop here and take a 10-minute break. And I'll be in charge of the seminar today. And what I'll like to do is to go over a problem worked out, and then we'll break in groups, and you'll do another problem, and I'll go through groups to make sure you can do it, and we can make these predictions. Let's stop here, and I'll see you in 10 minutes.